Thank you for your presentation, and thanks you all for coming. During this talk, I will present the work carried out in collaboration with Professor Jaime Planas, who is here, and with Professor José María Sancho at the Materials Science Department of the Universidad Politécnica de Madrid, Spain. And the title of my presentation is Study of the Influence of the Oxide and Concrete Parameters on the Results of Accelerated Corrosion Tests. The outline during my presentation will be the following. First, I will start with an introduction. Then I will explain the experimental and numerical methods, followed by the results and discussion, and finally the conclusions. So let's start with the motivation of my work. Corrosion affects reinforced concrete structures in aggressive environments and even can lead to spalling of the cover, as we can see in these examples. It occurs because there are some aggressive agents that go through the cover, for example chlorides, and then the passivation of the bars occurs. Then corrosion starts, and there is generation of an oxide layer. That means that part of steel is transformed into oxide, but there is also a volumetric expansion that produces cracking of concrete, and we call corrosion depth to this part of the steel. Well, there are many numerical and analytical models to analyze and simulate that effect, from Basant, physical model, Molina, etc., and including ours. But the problem with the models is that there are many unknowns about the generated oxide and its mechanical behavior due to the difficulty to perform direct measurements, so the parameters have to be assumed in the models. For example, the expansion factor depends on the type of oxide generated, but the problem is to know what oxide is being generated in real processes. And another example is the shear stiffness, which in previous studies, numerical studies, was assessed to influence the pattern of cracking, but there is no experimental information for this parameter. So the objectives of this study was to gain further understanding of the system steel oxide concrete, and for that we present a study using prisms with a tube. The methodology during this work is as follows. First, we carried out experiments using the specimens which were designed to get a dominant mode of failure consisting of a single main crack. There are other secondary cracks, but this one at the cover is much wider. And then we perform accelerated corrosion tests, record some variables while cracking is occurring, and after the test, we cut the specimens into slices to study the crack patterns along the tube. And in parallel, we carried out numerical simulations using a model that reproduces the concrete and the oxide behavior. And for the concrete, we did experimental mechanical characterization, and is used as input in the simulations. And for the oxide, we have to assume the values initially. Then we simulate the experiments, obtain the same type of results, compare them to those in the experiments, and modify the oxide parameters until the simulations reproduce the experimental results. And with that, we obtain information about the oxide. So now let me briefly present the accelerated corrosion test, because they are used as reference in this work, but you can find here more details. The idea is the following. The tests are designed to have conditions reproducible in bidimensional models, which is essential to compare with the results of simulations. And the specimen is submerged. We apply a toxic coating, isolate the strengths of the bar, of the tube, sorry, and then we obtain plain current field and uniform corrosion. We apply a constant current density during the test, and we record the following variables. First, the intensity, and from that we compute the corrosion depth, applied as Fahrenheit's law. We also record the main CMOT, that's the width of the main crack, measured at the middle section of the specimen, and for that we adapted a commercial extensometer. And we had other two special measurements. First, the variation of inner diameter, and for that we designed and fabricated ourselves some extensometers with the following idea. There is a flexible pin clamped to two rigid bodies that press at the inner wall of the tube. Then when there is a variation of inner diameter, there is double bending of the tube, and it is recorded, measured with strain gauges. And the other measurement is the height of liquid in a capillary. For that, we fill the tube with liquid, seal the strengths of the tube, except for that exit to a capillary. And then when there is, for example, a reduction in the inner diameter of the tube, there is an increase in the height of liquid at the capillary, so we measure that. These are pictures of the experiments. The first type, a test with a diametral extensometer, and we can see here the elements of the test, the counter electrode, a thermocouple. This is the diametral extensometer to measure the diameter, the variation at this diameter perpendicular to the expected main crack. And other elements, the maximum extensometer, a diagonal pilar, and a clamping frame to support this extensometer. And the other type of test is a test with a capillary circuit. And we can see here the reference frame, the glass capillary, a fluorescent lamp, some other elements as brass caps and metallic capillaries to fill the circuit and the vacuum, and also the maximum extensometer. Now I will briefly present the model to simulate corrosion-induced cracking. It has three ingredients. First, the concrete fracture, and for that we assume that concrete follows the standard cohesive model. And this behavior is implemented within the finite element program COFE by Sancho and Professor Planas. This behavior is implemented in elements with an adaptable embedded cracks, which is a strong jump within the element and can orient wherever, depending on the stress field. And the third ingredient is the oxide model. For that, we program expansive joint elements. You can find here the detail. And these elements reproduce the volumetric expansion and the mechanical behavior of the oxide, and also incorporate the bonding effects, first sliding by reducing the shear stiffness, K sub T, and second separation, diminishing the tensile stiffness with this directionality factor. So these are the parameters in the simulations, two types of geometries. First, bars, models with a bar as a reinforcement for preliminary results, and second, the stacked geometry of the experiment. And in all cases, the mesh was generated using this program, GMesh. Will record the displacement between the nodes A and B to simulate the curves of main CMOD. And for this type of geometry, we also record the displacement at the corresponding nodes for this variation of inner diameter, and at all the inner nodes of the tube to compute the variation of capillary height. For the materials, we use mechanical characterization parameters for the concrete, for the steel, the standard values, and for the oxide. Initially, we assume a fluid-like behavior as proposed by Molina, and nearly perfect sliding and free separation, and then we modify the parameters. So these are the results, the experimental results. First, the main CMOD versus the corrosion depth. We observe that the crack grows very slow during the first micron of corrosion depth, but then there is a break which indicates fully development of the crack. Okay? These are the curves of variation of capillary height, and what we see here is that there is a sharp increase at the beginning up to a peak that coincides with the corrosion depth of this break, and we call that critical corrosion depth. So that means that the tube diminishes its volume, and then when the crack develops, the volume partially recovers. However, the variation of inner diameter was almost increasing. That means that the formation of the tube is not uniform. If we simulate the results with the initial values, we see that the model captures the main trends of the experiment, but it is necessary to adjust the oxide parameters. For that, we carried out a numerical study. I will only show here the effect of the most representative parameters, but you can find the details in the paper of the conference. First, the expansion factor. These are the results for prisms with a tube of main CMOD, beta ranging from 1 to 2, and variation of capillary height, and we see that the expansion factor escapes the result. It is also observed in prisms with a bar, but the interesting point here is that the corrosion depth the critical corrosion depth is fit more accurately with this sharp peak than with this softer break. And also I will show the effect of the shear stiffness in the curves of main CMOD for prisms with a tube, and if we compare them with prisms with a bar, we observe that the effect is more noticeable in prisms with a tube. Moreover, the variation of capillary height and also the variation of inner diameter are much more sensitive to variations in the shear stiffness than the main CMOD. So that's essential for indirect determination of this parameter, because the shear stiffness governs the behavior at the peak. Then we modify the parameters, and I will show the definitive results for these final values and the other one as initially assumed. And these are the final curves. And now we see that the model predicts quite good the main experimental results, except for a few limitations of our model. For example, here the crack width is overestimated, probably to the possible effect of diffusion of the oxide within the cracks that is not implemented in the model yet. Also, this peak is overestimated, but it is also a consequence of the concrete parameters. Okay, in this simulation we see that with a down percent scaling of the softening curve, the numerical curves fits much better the experimental one, and it could be explained by the different conditions in the characterization mechanical test and in the accelerated corrosion test that lasted 3 days. And for the variation of inlet diameter, there is a high scatter, and it is influenced by the position of the main crack and uniform corrosion. So further work is in progress. I end my presentation showing the final pattern in the new simulations, which agrees well with that in the experiments of the slices impregnated under vacuum, which present resin. So to conclude, a method has been presented for a direct elimination of the mechanical parameters of the oxide. Using tubes as a reinforcement was crucial in this work. It's not realistic, but we have used that to obtain material information, and then we can use these parameters for further studies. Well, because measuring the variation of the dimensions of the tube provides essential information, and finding element simulations with expansive joint elements and embedded cohesive crack reproduce the real cracking, and values have been proposed for the cyclic parameters that could be used in further studies. So that's the end of my presentation. Thank you very much for your attention.